how the regularization term is used to reduce the high variance, or how it is used for eliminating the overfitting. We are taking the logistic regression, and this is the cost function for the logistic regression. We are adding an extra term which is called as a regularization term. This lambda is called as regularization parameter. So this is normalization of W. So we are taking the whole square. We are calling this regularization as L2 regularization. In this L2 regularization, we are taking the square of each parameter and we are summing up. But remember here, we are not bothering about the B. In the machine learning also, we have not considered the theta naught. Here also, we are not taking the lambda by 2m B square. Even though B is a parameter, we are neglecting it. We are only taking lambda by 2m W square because the design of the W we are looking for really. So we are adding it. This is called L2 regularization. In reality, in the L2 regularization, what we are performing? We are performing the multiplication of the parameter matrix W and its transpose. We are multiplying the W transpose with itself. It is giving a 1 by 1 matrix, which is the squared sum of all parameters. This is what we are doing in the logistic regression for implementing a regularization term. In the similar lines, we implement the regularization even for the neural networks also. We will see that. In the neural network, we have taken the cost function. This is having so many layers. So many parameter matrix W1, W2, and so on, WL. Here also we are adding lambda by 2, normalization of WL square, which is the L2 regularization. But here, because we are having L number of layers, we are adding the squared summations of all matrices for the L layers. That's why I am writing small l is equal to 1 to capital L, where this capital L is representing the last layer. And similarly, we are writing normalized value of WL square is equal to I is equal to 1 to NL, and J is equal to NL minus 1, where I is representing the rows and J is representing the columns of the parameter matrix. The I, how many rows are there? That depends upon the number of activation units in the Lth layer. And how many columns are there? That depends upon the activation units in the number of activation units in the L-1 layer. So we are using this W, which is having the matrix size NL by NL-1 with rows, number of activation units in the Lth layer, and columns. A number of columns as a number of activation units in the L-1th layer. We are taking this W and we are taking each and every element and we are summing up all the squared elements. Finally, we are getting the W square for each and every layer. We are calling this normalization as Frobenius normalization. So this is a technical name, Frobenius normalization. Now, finally, we want to get the DW. In this DW, we are implementing the regularization term as lambda by M into WL. With the addition of this lambda by M, WL regularization term, the DW value is incrementing. Because the DW is incrementing, the W is decrementing. So finally, we are achieving a condition that is the weights or parameters are decrementing. That's why we are calling it as a weight decay. But we are still having the doubt how the introduction of the regularization term is preventing overfitting. We are explaining that. For example, take a tan H activation function. This is a tan H activation function. Now we are introducing the lambda, and the lambda value we are incrementing. Assume the lambda value is high, and because of the lambda value is high, the WL value is decrementing. Because the WL value is decrementing, the Z value is also decrementing. Because the z value is decrementing, the tan h function value range is in the linear range, means this graph is linear only in the small portion of that range. Now because of the high lambda value, we are making the tan h to be in this small linear portion of that range. That makes our classifier to be linear. Now, before, the classifier may be non-linear, but because of this lambda term introduction, the regularization term introduction, this will be behaving like a linear in that small region where the z value is very low. Because the z, why? Because the z value is very low, w is very low. Why w is very low? Because the lambda is very high. This is how we are preventing the overfitting. Now, how to check whether we are getting the overfitting, how to check whether we are getting high variance or not. We have to check what is the crash validation set error. To check the crash validation set error, we will take the number of training samples of the crash validation set, and with the each iteration, we will check what is the error. If the error, crash validation or a development set error is very low, then it itself is an indication that the design of your system with the introduction of the regularization term has decreased the variance. Now this is a low variance problem. Now you can use this as to predict your output.